Okay, hi everybody. Welcome to our talk about Lambda and Lambda SnapStart. So it's the 10th anniversary of Lambda this year, so really excited. It's been around for 10 years, so I thought I'd start with a bit of a quiz. So how many people in the room are writing Java code as part of their job? Lots of you, not super surprising. How many of you are running that Java code or have ever run that Java code on a Lambda function?
Oh.
Still a lot of you, that's awesome. How many of you who are running that code on a Lambda function have ever used SnapStart? A few fewer of you. And so I think that's good. We'll talk to you a little bit about how SnapStart works today and how we built it under the hood. But I thought I'd kick off at this sort of 10 years ago, we designed Lambda. 2 years before that, Werner, our exalted tech leader, made this bold statement that in the future you'll only write code, you'll only worry about business logic, and that's really, really awesome. And more recently, our CEO also made this other statement that there's no compression algorithm for experience. If you're writing code, it's kind of hard. You're building technology, and you've got to kind of go through the trenches and earn your scars. And so controversially, I'm going to say that maybe Lambda is a compression algorithm for experience. But I thought we'd start with a demo because we've got some experience. We've got a few scars, Mark, so we know that demos in talks always work out really, really well. So let's kick it off as we need to go on and show you a little bit about how all this stuff works.
So everyone cross their fingers. So what I've got today is just a really simple demo of a performance test. So what we're going to do is going to compare a Java Lambda function with a certain benchmarking profile. And we're going to do it with and without SnapStart. So super easy. We're going to start from a completely flat baseline. So this is a Lambda function with no running instances, if you're familiar with Lambda, but basically from zero. We're going to immediately go up to 100 requests a second and then scale up to 500 requests a second really quick. We're going to stay at 500 requests a second for a while, and then we'll have a look at the results afterwards. So this Lambda function is a Java Lambda function. It talks to one of our database services called DynamoDB, and it's just putting some data into a database. So it's not a hello world, but it's not like a 2 million line monolith either. This is a function to put data into the database. So what I'm going to do is going to make this bigger to start with. And yeah, I'm using Artillery. Probably people familiar with Artillery. It's a very simple benchmarking application. So I'm going to go from 100 requests a second to 500 requests a second, and then stick at 500 requests a second for a while. And I've got two EC2 servers, basically, who have got a fair bit of networking, a fair bit of CPU, and I'm just going to blast all this traffic at them Lambda functions now. And then at the end of the talk, we'll cross our fingers and hopefully the demo will be awesome, and I'll be able to show you the difference between two performances.
Cool. So going back to that kind of Werner's big statement, in the future you're only going to write your code, the kind of mental model that AWS adopted, the kind of tenets about how we actually go and execute this is this idea of the shared responsibility model. And in serverless world, we take on the most amount of the shared responsibility model. So on an EC2 instance, we're looking after your infrastructure and your racks and boxes. In a serverless world, we are actually managing your compute ready for you, running a runtime. You're also typically combining that with storage and databases, things like DynamoDB and S3. We've also got that kind of messaging and orchestration. So all of our application integration services like SQS and event bridge and step functions are probably gluing all that together. So what you should be thinking about is what are the APIs and event schemas that define your application, and what's the business logic that you actually use to run them. As I said, because we're taking on that shared responsibility model and a whole bunch of AWS experience on how to run and operate these distributed systems at play, we might call it a compression algorithm for experience. It might get me fired, but you never know. But essentially, we give you a way to provide a jar file or a zip file or an OCI image. We'll go and execute it. You pay by the millisecond that it's actually executing. We provide this runtime for you. You don't have to think about managing your servers. And we can scale up in milliseconds to changes in traffic. It's a decade old. At some point we were the cool new technology at AWS. Now it's something that almost all of our customers use, and a million of them are doing it. and something like 10 trillion Lambda invocations every month. So it's super powerful stuff. Really briefly, yes, different from a typical Java application where you've got a web server listening for traffic. We've got our compute, it's waiting for some event, which might be a change in state or some other kind of event. Goes and does some compute, it might connect to some downstream services. We've got a few different models. There's a synchronous model where maybe you're building an API. We've also got asynchronous models where if you're doing something that's processing off the back of a queue. I think that the poll base is a really powerful model that not that many people necessarily understand, which is if you're consuming something from maybe a streaming source, maybe a Kafka stream, we'll actually manage a fleet of pollers who are going and polling that, who are managing your event horizon, or scaling in and out the Lambda compute to be able to process that stream. And we give you all that to use as a completely managed service. Really useful model. When you're in a Java world, the kind of native way of doing this is you get an object, you get a strongly typed Java object that represents the event source. So it might be an API gateway request, it might be an SQS event, it might be some document event from S3. That object gets passed to a handler. You can go and do some code with it. We also, when we start to do this in a kind of the real world of building Java applications, there's actually a lot of abstractions that's done by frameworks. So if you're using something like Spring Cloud Functions or Micronaut or Quarkus, they'll abstract away a whole bunch of that AWS evented model. So something like Spring Cloud Functions will allow you to use some generic Spring functions that are wrapping those AWS specific classes, allow you to have some lightweight routing, gives you this kind of really simple type conversion, and so you can compose your Spring Cloud functions, and they're very portable, moving them between different places. So essentially what that looks like is there's this abstraction layer on top of your application code. There might be Spring Cloud Function or Micronaut or Quarkus equivalents. But of course, lots of people are building their code using kind of controller model and using kind of Spring Boot applications. So you can run those on Lambda really well as well. So in this world, we have an adapter that is going and taking maybe an HTTP type JSON object from API gateway. It's converting that into something that Spring understands, and then going and routing that to your application code so you can use that normal familiar programming style, or maybe move an application that's running somewhere on a web server or on a container over to Lambda. And so this is a project we work on in collaboration with Spring. Recently hit 2.1 release and now supports all the sort of latest versions of Spring. And so this is a sort of collaboration between us where we handle all the deserialization of all those AWS objects. We hand it over to Spring. They then convert it over to the right objects that works with Spring security and all the other good stuff that Spring does. One of the sort of really powerful bits of Lambda is this scaling model. So it's super simple model. We process one request at a time. So if a request comes in and an invocation environment is busy, we'll just give you another fresh invocation environment. And that helps us have a really simple scaling model. So if you're in a kind of traditional on-premises world, you have to go and order how many racks you need. You have to over-provision like crazy because you're going to have to deal with Black Friday. And then if you haven't ordered enough for Black Friday, you've got a giant problem. So moving to the cloud, it solved a whole bunch of that. But if anybody's ever tried to manage auto-scaling groups on EC2, it's non-trivial. It's really easy to shoot yourself in the foot and end up with either too much capacity and get a call from your FinOps guys, or not enough capacity and not be able to deal with the spikes. With Lambda, we try and scale as closely to your application traffic as possible. So that means when there's no traffic, we'll scale all the way to 0. We won't send you a bill at all. And we can scale up to thousands of execution environments really quickly. So this is kind of new scaling behavior that's recently been updated and consolidated in the last sort of a few months. But now the scaling behavior is we'll give you 1,000 execution environments every 10 seconds, all the way up to your account limit. Those account limits are soft limits. So, conceivably, you can scale up to something like 40 terabytes of RAM, 24,000 cores in just a few seconds. Jonathan there, who actually has to make sure the capacity is available, squirming in his seat slightly. And we can scale these huge amounts of compute faster than anything else on AWS. Of course, if you're running a big kind of HPC grid or a big Kubernetes cluster, you can get more compute eventually, but it's going to take you hours, maybe minutes in best case scenario to get to that level, and Lambda can get there just in less time it takes to make a cup of tea. So a big picture of what Lambda is. I'm going to hand over to Mark to talk a little bit about some of the design principles we use when actually engineering this.
Yeah, so I'm going to talk to you a little bit about how we've designed AWS Lambda, but let's think about what were our fundamentals, what were our tenets when we were building this system. So roughly these are our 5 tenets. So availability has to be highly available by default. So AWS runs in a number of availability zones. AWS Lambda is by default running in all of those availability zones and giving you fault tolerance and high availability at all times. If there is any sort of issue, it will automatically go to a healthy place to run your code. Efficiency, we really don't want to be over provisioning hardware. It'd be very easy just to throw more and more hardware at the problem. And that isn't efficient for us. It isn't a good idea to burn a load of electricity, a load of carbon, and also we don't want you to pay for that inefficiency. So efficiency of compute is really important for us. And there's a lot that we can do with data science to make sure that we provision your compute in the right place and are optimal for that. And just as Matt was talking about scale is really important. The faster that we can scale, the less capacity you have to hold. Okay, so the faster our scaling behavior is up and down, the better we can match your user or your customer workloads, which again drives efficiency. So this is all a super virtuous cycle. Obviously, security is job zero at AWS. Security is our first tenant, and Lambda is something that really, I think, benefits the security side of running applications. You know, we are responsible as AWS for patching the operating system and the runtime. So, you know, I've worked with financial services customers who say that they spend, 12% of the team's time is spent patching servers and containers. You know, that's something that, that team can now focus all of that time on building applications instead of looking after security. And again, lastly, performance. We want to build a very high performance system because the faster the code is running, again, the more efficient we can be, which helps us to do the scaling. So these all are very, very interconnected. Okay, so this is a rough architecture diagram of Lambda. And we would be here all day if we went through it all. So today we're just going to focus on 3 sections, which is how we do invoke routing, how we actually find machines to run code on, which is what we call compute fabric. And we're going to talk a little bit about SnapStart, which is one of the newer features that we have to help improve performance for Lambda. Okay, so let's dive into invoke routing. So, imagine yourself in this position. You've got these tenants, and on day 1 of your new job, we're going to build AWS Lambda. So what are the first sort of things we're going to do? Well, we want a very easy way of onboarding people. We want to take their code and some configuration, so maybe what version of Java they want to use, what method they want to invoke, what memory and CPU they want to have allocated to that task, maybe some environment variables, maybe some other configuration. And we're going to store that in a microservice. So we're going to have a microservice just responsible for configuration. So this is going to know the location of the code in S3 and how the environment should be configured in order to run the application code. That's all ready. That's all been saved. Alice is now able to make a request to say, run my code. And that goes to a microservice called the front end. In collaboration with the configuration service, we've now got everything that we need to run that on a worker. But how does the front end know where to run that code? So what we do is we have a placement service. So the placement service knows how to create what we call workers and sandboxes. So a worker is a machine, and sandbox is an isolated environment that can run the application. So placement finds somewhere to run the code, sends that to the front end, and the front end sends that input, and the code runs on the sandbox. It's quite a lot of steps there. And actually, thinking about this, this is a user time, right? So this is an on-demand system. This is a system that's trying to be super efficient, not hold spare capacity. So all of this has to be done while the customer request is in flight. The customer is going to be waiting for a response. So all of these different steps have to happen before the customer response returns. And there's kind of two sections. There's, the stuff that AWS can be responsible for, which is, how fast can we find a server to put your code on? How quickly can we get that code onto that server? How quickly can we start, in our case, Java, the runtime? And then there's the part of the code that you're responsible for. Your code needs to initialize fast. It needs to be ready to run the input that comes to it. And we're going to have a little look at this histogram over the next few slides, but this is basically going to be the number of requests and the amount of latency for each of those requests. And the invoke section is basically the useful work that the customer wants to do. And really, our histogram should be around this area. That would be the ideal situation, is that all of the useful work is happening and AWS isn't really contributing much to any additional latency. But what's actually happening is that we have to run through a set number of steps in order to make sure that we have the infrastructure ready to run your code. So this is, initializing sandbox, getting your code onto that sandbox, runtime, etc., etc. So we end up having a bell curve at the end of this. And obviously you can see that this isn't the most efficient thing. It's actually quite an easy optimization that we can add here, which is called the worker manager. So the worker manager knows which workers have been created in the past, and we can keep them around for a set number of time, and we can say, oh, actually, Alice's code ran here previously. We'll just run the next invocation on that worker. It's all ready to go, and actually we can skip a load of time. So we've now got two modes of operation. We've got like a fast invoke path and a slower path where we're having to initialize a new execution environment. So now the histogram looks a little bit different. We've got the warm invoke path, which looks like the ideal situation. Most of the work has been done, is the customer's code, and that's the ideal situation. But unfortunately, we still have this second mode, which is the cold starts, where we're having to create new execution environments. There's a whole depth to the worker manager that one of our senior distinguished engineers goes into even more detail. So Mike Danilov recently did an amazing talk at QCon San Francisco. I would definitely recommend having a look at this.
You moved on too quickly, Mark, from the QR code.
Oh, sorry.
Volker didn't get the...
It's a good talk. It's a great talk.
Great. So Mark was talking a little bit about the invoke routing. The next kind of really important bit is the compute fabric. So we've got some stuff that comes in. We've got to somehow go and place it on our worker. And so now we've not only got Alice's code running, but we really want to be very, very efficient. So that means actually building a multi-tenanted solution where we can share this infrastructure across multiple customers. So Alice's code is running, Bob's code comes in. Where are we going to place Bob's code with Alice's code already running? And we've got a few options. We could actually go and run all of their codes as separate Java applications inside the runtime. That would be great. It'd be super, super efficient. We wouldn't have to spin up any new compute. However, alarm bells kick off on our security tenant. And we've basically got no isolation, and Bob can do all sorts of stuff with Alice's memory. And we're not happy about that. The next model, how customers are building single tenant systems at the moment would be, let's go and containerize these and potentially let's have them in a Docker image or some sort of separate runtimes. We're going to try and isolate these runtimes and somehow we're going to be able to use this to make that code completely isolated and secure. And lots of people have been trying this and it's a really, really promising space. However, as of today, it's not meeting our bar for security, so we have to discount that. So what we're left with is actual virtual machine isolation. Virtual machine isolation is incredibly tried and tested, absolutely really, really rigorously used across technology and actually does meet our bar for security. So that's great on our security tenant. However, it has some challenges against some of the other things that Mark was talking around, particularly around efficiency, performance, and scale. These virtual machines are much more heavyweight than just having a process or an application running in runtime. So one way to solve that would be to have single tenanted VMs. So we can have Alice's EC2 instance, and we can have Bob's EC2 instance, and we can start putting their code into that single tenanted EC2 instance. And it runs for 30 milliseconds, then nothing happens, and then we've just got waste. And so that's not meeting that efficiency. Efficiency tenant. We could also, maybe Alice has got more than one function. She's got 50 functions, she's got 100 functions. Why don't we pack all of her functions into a VM, and then maybe we can get better efficiency out of this fleet of boxes that we're running. However, when we tried that, there are some challenges around that. Let's say Alice has got 50 functions as part of our application. A flood of traffic comes in because it is Black Friday. Funnily enough, all 50 functions need to scale out at the same time. So we get this highly correlated demand with a single tenant customer. So actually, we need to have a way that we can spread Alice's load across our fleet of instances in order to spread that demand really flat across our fleet in order to get to meet our tenants. So thinking about how to do this, AWS went away and created something called Firecracker. So that is a way that we can create these very, very secure micro VMs that are incredibly lightweight, that can start up in tens of milliseconds, but have all of those benefits of a VM model. And by doing that, it enables us to give customers access to all of those runtimes I mentioned at the start. So these are POSIX VMs that can run Go or Java or Python, and give customers lots of freedom to run their codes in that environment. So on Lambda, we've now got essentially our host kernel VM. So we've got some sort of bare metal EC2 instance under the hood. We're now able to create a sandbox, which is Firecracker lightweight VM in that instance. And we can now get hundreds of different customers running different functions all in one base kernel instance. So give you an idea of the scale. So lots of the fleet that's running Lambda are these big EC2 M5 metal instances with kind of almost 400 gig of RAM. Our smallest Lambda function is just 128 meg of RAM. So it's like 3,000 times bigger on these bare metal instances than the individual customer functions. But of course, they're not all 128 meg functions. We can run anything from a 128 meg function to a 10 gig function. And because we've got all these different sizes of functions, we're able to really efficiently pack all of those things, and we can use all sorts of kind of machine learning, data science, and statistical methods to make sure we've got a really even distribution and we're not correlating all that load together. So the Firecracker, it gives us these big benefits of it gives us very, very strong isolation boundaries. It gives us a low system overhead. It allows us to achieve that statistical decorrelation when individual customers scale. And so that's taken this cold. Can't really see it on my screen here, but it's taken our cold start from there, and we've shifted it slightly closer to our warm invoke. So that's great. Now, in a Java world, lots of that initialization, runtime, code execution is actually the customer's responsibility. So in lots of our interpreted languages, we get going and we start interpreting a node script and it's off and running. But let's say this is a Spring Boot application using Java Serverless Container that I talked about at the beginning. In that world, we've got your VM ready, we've got your JVM ready, you've now started running your code, and Spring's going off and doing a whole load of runtime dependency injection. It's going and connecting to a whole bunch of databases. We've pulled down a huge XML file that contains a whole load of data that we need for our application. We're going and doing all that. So how do we start to get rid of all of this additional cost, which in the Spring Boot application could be 10, 12, 15 seconds? So back over to you, Mark.
Yeah, and I think that's really interesting because, if you think about this from a systems point of view, we're doing the same task over and over again. So we're taking an execution environment, we're downloading the code, we're starting the JVM, loading the code in, we do all of that work, and then when we need another execution environment, we're just doing the same work again, and we're just duplicating the work over and over again. So, what would be a better way of doing this? Maybe instead we can determine that when an application is ready, then take a snapshot of that application in its fully ready state, and we can store that snapshot in some sort of storage mechanism, in a cache mechanism, and can we then restart that application from the snapshot faster than actually booting up Java from scratch? So that is the idea of Lambda SnapStart. Can we take a snapshot of an application and resume it later faster than normal? So now you're able to tick a configuration item on your Lambda function to say you want to enable SnapStart. You create a Lambda function version when you upload some new code, and instead of allowing immediate customer requests to that function, we're going to take that function off onto a separate worker and execute your code. So we're going to load your code onto that separate worker, boot up your code, let it get ready for your application use. You can run whatever code that you need to in order to make your application as ready as possible, and then we'll take a snapshot. Okay, so how would we build that? Well, this is the back of the envelope style drawing. So yeah, we're going to take a snapshot of that entire virtual machine. So the Firecracker virtual machine, we're going to take that snapshot file and we're going to put it into our object storage S3. Later on a completely separate worker, we can download that image and resume it into lots of different virtual machines. Turns out that those virtual machines can actually be quite big. So obviously your Lambda function can have up to 10 gigabytes of memory. And then you've got the disk images and some state as well. So actually it becomes a fairly interesting problem. So let's summarize. So we need to take snapshots, we need to distribute those snapshots, resume them, and we also need that to be faster than our on-demand system. Okay, how do we do that? Well, once the snapshot file is on the worker, we can use various techniques from the virtual machine to map different parts of the snapshot file to memory and disk. But these are complete clones, okay? So these are exact replicas of the original, which kind of, tingles some bells in my head. I'm like, well, some things need to be different. And a good example would be random numbers. So random numbers need to be seeded differently. We can't have the same sequence of random numbers being generated on machines. That would break cryptography. It would break identifiers for databases. It would break all sorts of stuff. So we need to make sure that at every stage of the software development cycle, we're looking at how to maintain uniqueness in these environments so that when we resume a snapshot, we're not breaking customers' code. And that's where we've worked quite closely with open source communities to make sure that we're really looking into this. So we have committed changes to OpenJDK, OpenSSL, and Linux to make sure that these sources of uniqueness are seeded correctly so that you're not getting predictable numbers.
So Mark's talking a little bit about how we generate the snapshots, how we make sure that they're secure. Kind of last big design challenge we'll think about is how do we load the snapshots. So Mark said that showed that these can be really big. You can upload a 50 meg Java file in your Spring Boot application and generate a snapshot that's conceivably 30 gigs big. So even on our big bare metal instances, downloading that snapshot to the instance could take 10 plus seconds. Actually, we're slower than we were using our additional on-demand model. So we want to really avoid this process of just copying massive files around to hundreds and hundreds of workers. But we know there are processes to do this. So actually, do we need to have the whole snapshot available as soon as your function is started? Maybe not. Maybe we could do some sort of dynamic response streaming, so we could start to stream that file to the worker and only just have it there just in time for it to be used. And one of the ways that we do that is we take this single snapshot, we divide it into a whole bunch of chunks, so divide it into 512K chunks. And each of those blocks sits in a manifest. And as we execute your function, we start to optimize the load order of this manifest. So when a read comes in, instead of reading directly from disk, we go to this indirection layer. That indirection layer then goes and loads that block. It might go and load that block from a local cache that's on the host and is super fast. It might go, hey, that block isn't available on that local cache. let's go and look at the distributed cache, and maybe there's something that's in the availability zone that's available to go and load that block. And then finally, we've got our origin, so we've got highly available S3 bucket that's containing the full snapshot, and it's a kind of last option if we haven't got that block available. So we've got a very, quite a big distribution in our cache access time between calling all the way home to S3. We really want to avoid that, and these really, really fast cache hits we can get from our local cache. So what we really want to do is think of a way that we can really optimize that local cache without having to store millions of customers, 30 gigabyte cache, 30 terabyte snapshots on all of these images. So what we'll find is, we've got Alice and Bob's code, that actually a lot of those chunks will be the same. They're almost certainly both using Amazon Linux 2 base images. They're both using Java JVM. They might actually be sharing a whole load of common libraries that have got the same bytes in those classes. So we can actually use some correlation encryption, and we can go and share those blocks. So actually, there might be the blocks that are part of Amazon Linux 2 that can be used for all of those customers. And those are probably already in the local cache, and they're probably shared again across everybody who's using it. For the runtime, so that Java 17 runtime, those are also likely to be already in that local cache for all the customers. And then what we get is then actually the bit that we care about, that unique stuff, is actually the function code, and that's what's getting cached by your function. And obviously, as your function starts to get used, and you're starting some sort of scale-out behavior, we'll start to hydrate those caches. So if you're getting a big spike in traffic, you might start with some slightly longer cold starts than your future cold starts. As you have that scale-out behavior, will get warmer and warmer and warmer, and will get faster and faster as you start to hydrate the caches all the way across the fleet. So that starts to bring, from the beginning, everything was a cold start. Then we introduced our kind of worker manager, and we managed to have warm starts and cold starts. Then we did our optimizations with Firecracker to reduce that cold start time. And now we've used SnapStart, and we've brought it even closer. Have we solved cold starts? Not yet. There is still some difference between those hot invokes, and Mark will show some data, be a single-digit milliseconds for our warm path, and hundreds of milliseconds for that cold path. But we're getting there, and we're working on it. And obviously, there is all sorts of smart people working on how to get it even closer to that warm route. But when we go back to those principles that we looked at, I think it's really interesting to go and take a look at each of those services. So we've got invoke routing. We're really trying to meet that availability and scale principle. Our compute fabric, we've really been focusing on efficiency and security. And this ongoing work to address cold start is really looking at that performance tenet. So that's taking us back to that place where you only have to worry about your business logic, and I think that sort of shows my argument that maybe Lambda is part of the compression algorithm for experience. That this Lambda team is out there doing all this cool stuff, working out how to optimize their compute, all this stuff that's really, really complicated and difficult to do, and inventing new technologies, new VM technologies, new ways of storing snapshots, new ways of sharing encrypted blocks across multi-tenanted systems. All of that is helping you get all the benefits of this system, whilst you're really focused on being an efficient Java developer. So at this point, I think we might have the results of the tests that kicked off at the beginning. So hopefully that ran okay, and Lambda scaled beautifully, and we got some data.
Okay, so what I'm going to do is I'm going to take us to Amazon CloudWatch, which is where we do a lot of dashboarding and logs and metrics. And I'm going to show you a little custom dashboard that I made. So let's change this a little bit. Let's go to the last 45 minutes. And this is basically showing the requests that are coming in. So on the left-hand side, we've got invocations on the Lambda function without SnapStart. And on the right, we've got invocations with SnapStart. It's the same. It's the same number of requests, same rate, all the same, coming from the same source to the same place, same code running, should be the same. The next set of graphs is what we call concurrency. So this is the number of virtual machines that are allocated to handle that request traffic that's coming from my synthetic benchmark in this case, but customer traffic. So you'll see on the left-hand side that there's this huge spike because each time without SnapStart, it takes us a lot longer to provision an execution environment, a sandbox. So when I started the benchmark, I started at 100 requests a second, and I just went straight up, straight up to 500 requests a second, which means that to handle that code, to handle that traffic, I had to scale up to 300 execution environments. Okay, so that is definitely different to the other side. So on this side, I only had to go up to 55 execution environments. So from an efficiency point of view, you can probably imagine that, that burst scaling, we went from 259, but then as soon as those execution environments were ready, we're dropping down to 21. So there's a huge difference of actually those execution environments that we spent all of that time building, we're actually just going to end up parking because we don't need them for the current traffic profile.
I think it's also really interesting that from his original test, we're actually doing 500 requests a second are being served because once Java's up and running, it's really, really fast. We're taking multiple requests a second out of each individual execution environment. So we're doing 500 requests a second, with 20 concurrency, and we can scale up to thousands of concurrency. So the kind of scale that we can actually get to in a few milliseconds if you're building real-world applications is really amazing.
Yeah. I could have a whole heap of EC2 servers throwing enormous amounts of traffic at this. I can scale a 1,000 execution environments every 10 seconds. The amount of traffic that I could throw at this and it would handle is awesome. Compared to when I was a programmer building systems on-prem, it's very, very different. Okay. The next graph is latency, but it's kind of hard to see on these graphs. So what I'm going to do is I'm going to jump into the logging part of the CloudWatch, and I'm going to run some queries against the logs that are generated by Lambda. So let's start without SnapStart. So let's close that for some space. So this allows me to run an SQL-like query to do some data analysis of the logs that are produced by the system. So it's going to go look at about, 300,000 invocations, and let's have a look at the performance profile of those requests. So you can kind of see the scale up at the beginning, and the query is separated the data into two rows. So the top row is all of the cold starts. Okay, so this is all of the code paths that had to create a new execution environment. So in total, we had 259 cold starts, which is the same number of concurrency we had on the previous graph. And our P50 latency for our customers was 2.8 seconds. Our slowest requests was 3.6 seconds. So there's a fair range in that. Some people, it's pretty fast scaling, but we always like to try and improve. But our warm starts, this is single-digit milliseconds. This is talking to DynamoDB, putting data into DynamoDB, receiving response from DynamoDB, and responding back to the customer. So
and actually, that's significantly faster than you typically get from running a node or a Python Lambda function. So actually, from the vast majority of your requests, if you're writing in Java, are really fast.
Yeah, absolutely. Let's have a look at the SnapStart data. So it's coming in, number of requests, again, same number of requests, around 300,000 requests. But look, it's just completely different. The number of cold starts or resumes from Snapshot is just a whole lot smaller. So we've gone from 250 odd cold starts. Now we only have 53, of the cold style of requests. And each of those requests is a lot different. So the average of those 53 colder invokes was only 890 milliseconds, and our coldest or slowest request was 1.2 seconds. So you can see that there's a big shift in performance, which is again brings onto that efficiency and cost saving aspect. And then again, the warm invokes, nothing has changed from the warm invokes. We still have that same single-digit millisecond response time from 6 milliseconds, and then the slowest of the warms, 28 milliseconds. So I think that's...
Yeah, and I think that this is a new function that Mark deployed just out there before we came into the talk. So obviously, when it's freshly deployed, all of those layers of caches haven't been populated yet. So, and you do this initial test, you get that kind of distribution where some of those slow caches are calling back to S3 for most of the code. Actually, as your function runs over time, and the more well used your function is, the closer you get towards that left, and the distribution kind of clusters around that P50.
Yeah. So if I imagine if I did a separate analysis of those 53, I imagine the slower ones would be nearer the beginning of the cycle, and then you would see the caching that Matt's talked about. And probably at the end of the cycle, you'd probably see more of the 890 milliseconds. So if this is interesting to you, please have a look at our website. We put a lot of interesting content on serverlessland.com. Serverlessland is where we put all of our serverless content. And there's a search bar, search for SnapStart. You'll find a whole heap of interesting stuff. Migration information, how to migrate Spring Boot applications from wherever to Lambda, information about how to run Spring Boot effectively, whole heap of information and patterns and blueprints to get you started really quickly. Everyone got a copy? Yeah, cool. So thank you very much. These are QR codes for mine and Matt's LinkedIn. We'd love to speak to you. If you're using this or trying this out for the first time, let us know how it goes. If you're finding any problems or any issues, we'd love to hear from you. Thank you very much.
I think we got... I think we've got a few minutes for questions, if anybody wants to know anything.
Just a remark, because this is an advanced talk. What was a bit disappointed that you didn't mention what I read in another presentation, that you're using crack internally.
Mm-hmm.
And what my experience is that without SnapStart, my Java application was unusable slow. So then with SnapStart it came, calling me 6 seconds start time. It makes some stuff. And then I implemented a crack hook, which preloads at least every Java class which is usually used. And with this I bring it down to the half to 3 seconds, which is okay. And just want to know if it is...
Yeah, I think that's a great point. I think there's always stuff that we include and don't use. I think that so there's a couple of technologies that are doing snapshotting that exist. One of them is SnapStart. It's a VM layer technology that snapshots the Firecracker VM and hydrates it. There's also, Azul have got an amazing technology, Crack, which does that at the VM, at the JVM. Volker, feel free to jump in.
Yeah, I can say some words on this. So you're right, SnapStart is using the Crack API, but that's basically just the Crack API, the before SnapStart and after restore callbacks, which SnapStart implements. But Crack is differently from technology point of view because it uses CREU to snapshot the OpenJDK process. So as Mark and Leslie explained, SnapStart is using Firecracker under the hood, which is the full KVM virtualization. And we take a snapshot of the whole VM, of the full KVM virtual machine. So we are not using CREU like the Crack project. We're also not using a modified version of the OpenJDK. We are using the standard Corretto version which you can download for SnapStart. So that's the basic differences.
But you are correct in saying that there are all sorts of interesting techniques that you can use in the before phase. And I alluded to it, but no, I didn't go into detail. But if you go onto serverlessland.com, all of the patterns that we have for SnapStart, include information about how to do what we call priming, which is making sure that your application is ready as possible for that snapshotting process. It's also in the blogs that we have on serverlessland.com. So I'm sorry we didn't go into it, but
there's also, I'm also interested that if you've got from 6 seconds to 3 seconds, you should be able to do better.
Yeah.
I'm sure there is
Talk
things
to us
we'd love
afterwards.
to talk to you and work
Yeah.
out why you're only at 3 seconds.
Yeah.
So the priming as a concept is, and we talked about what your customer responsibility is. You're running a Spring Boot application, let's say, it's loading some dependencies, it's got a whole bunch of code paths. It also might be connecting to things. You need to go and execute those code paths before they're stored in the snapshot to get the best performance benefit. And if you're connecting to remote things, you might actually want to go and connect to a service and then retry it and kill it. So if you can go and exercise all those things before your snapshot hook, then you should get significantly better performance. I would say that 3 seconds there's probably something else that is happening post snapshot that may or may not be required. That you might be able to
let's have a
optimize.
chat. And it means that we've still got work to do. There's still things that I would love to do with other AWS teams to help make that process easier. Can we implement crack APIs in some of the SDKs that AWS own, for example, so that the customer doesn't have to be aware of some of the extra steps? Can we make the best practice become a default? So
there's another question over there.
Our experience is that snapshot introducing it did dramatically reduce but it doesn't stop the first request being slower. Because you've got hotspot, it's still warm-up based hotspot is still quite significant, and you don't get enough time in that initial phase to be able to make a meaningful dent on that. You only get up to 10 seconds.
not with SnapStart. No, you have 15 minutes. So again, we seem to need to update our documentation. But yeah, let's have a chat. So you.
When we first did it, we've got to do it in 10 seconds. Limit rate what you can do.
Yeah.
You've got the full 15-minute execution time, so you can actually do quite a lot of significant work. And we've got customers doing some really wild stuff in that 15 minutes to prepare you.
Yeah. So we have a customer who we interviewed on YouTube who's downloading ML models onto the machine. They're being snapshotted, and he's able to move from VMs to Lambda because he can have all of that stuff pre-baked into the snapshot. It's loaded on demand, and his startup is able to meet his business requirements and costs identically. So
That's basically our requirement. Interesting.
yeah, let's have a chat afterwards. Cool. Thank you very much.